All right, let's learn about the concept of critical angle here. This is a consequence of the laws of refraction that we've looked at already, okay? So the concept of the critical angle. Where we're going to start, so we're going to start by thinking about what happens when light, or even water waves, I guess, switch from one medium to another, okay? So if we have an interface like this, and we have a wave that is traveling out of a slow medium and into a fast medium, what we're going to find is that there will be, if I put the normal here, there will be a bending of the light rays, if you want, or a refracting of the light waves away from the normal. So now we're coming from a slow medium to a fast medium. Okay? In terms, if this is an optical medium, okay, N1 would be high, right? The slower light travels, the higher the optical refractive index is, and N2 is low, okay? So low velocity into high velocity, okay? We have Snell's law in place. We also know this, right? V1 over V2 is the same ratio as theta 1 over theta 2, wavelength 1 over wavelength 2, and then N2 over N1. In other words, coming from an area of low velocity to an area of high velocity, right, causes a lower angle to become larger upon refraction. Okay, so that's kind of borne out by the math and by experiment, because the math is based on experiment, so that makes sense. So we'll get this kind of a scenario happening here. Okay, so this is our angle of incidence, and this is our angle of refraction. Of course, always measured from the normal. Oftentimes people forget that it's measured from the normal. You got to remember that. This is our incident angle, and this is our refracted angle. All right. So, my question to you is, if we continue to increase this incident angle, in other words, we bring the beam of light or the waves to a larger and larger incident angle, eventually we're going to get to a point where theta 2 gets large enough that it interfaces with the surface between these two media. Okay, so as this increases, eventually we get to a point where theta 2 becomes 90 degrees. Are you with me? The angle at which theta 2 reaches 90 degrees, okay, is called the incident angle at which theta 2 becomes 90 degrees. Is called the critical angle. Okay, so I'm just going to write that down, and then we're going to do some math with it. The critical angle, it only occurs, right? It only occurs when you're going from slow to fast medium. The critical angle occurs when you have waves moving from slow to fast media, from a slow to a fast medium. Okay. It is the angle of incidence, which causes the angle of refraction to reach 90 degrees, or, if you want, parallel to the surface. And this 90 degrees is, of course, from the normal. So I'm just going to draw another picture of that so we can see what I'm... So again, just to make clear what we're doing here, we're going to bring this down, right? And that is going to happen when we've reached some angle here, okay? Some incident angle here. When we reach an incident angle such that theta 2 equals 90 degrees, we call the incident angle the critical angle. What do you think happens if we get angles even larger than the critical angle? What must happen over here? What you get is you get a reflection, right? The light, the waves, cannot escape from inside the slower medium, okay? When you exceed the critical angle, you get what is called total internal reflection, okay? So I'm just going to write that down, and we can address any questions people might have. Total internal reflection happens when the incident angle, that's a symbol for angle, incident angle exceeds the critical angle. We're going to calculate the critical angle right away. So let's use this newfound information to talk about diamonds. So yesterday we learned that diamonds have a refractive index that is very high. And that value for refractive index was, do you remember? Good. N, and I'm going to put sub D so we know it's for diamond, ND equals 2.4. In other words, light is traveling like 2.4 times slower in diamond than it is in air, okay? So what I'm going to ask you to do is find the critical angle for diamond in air. Okay. So it's still going to be Snell's law. We're still going to use n1 sine theta 1 equals to n2 sine theta 2. And I just want to draw a picture of what we mean here, okay? Here we have light that's inside a diamond, okay? And what we want to know, all right, the light is traveling outward from the diamond. We know that the n value within the diamond, the refractive index, is 2.4, okay? We've also stated that since air is so close to being, or the speed of light in air is so close to being that in a vacuum, that we can consider the air to have an n value of 1, okay? That will not always be the case. So for instance, we might ask the same question about a diamond that's been put into water, and then something different will happen, okay? But anyway, light is traveling out from inside the diamond and it is speeding up. So what that means is, this is theta 1, okay? And what we want to know is, at what point, at what value of theta 1, do we get a 90-degree angle here for theta 2, okay? If we extend beyond that critical angle, then we have total internal reflection and light cannot escape from the diamond, okay? The light will bounce back inside the diamond when that happens, if we get above that critical angle. So let's set this up with Snell's law and just see what we get. N1 sine theta 1 equals N2 sine theta 2. Now what value did we say we would be looking at when this value is the critical angle? What value did we say theta 2 would be at? 90 degrees. Okay, so now we're going to substitute in what we know. And what is our n value for n2, or what is our value for n2 in this case? 1. Okay, it's 1. So what we would get then is we would get n1, which we know, sine theta. Now I'm going to change this to sine theta critical because that's what it is. When this is set to 90, this becomes that special angle called critical angle, equals, in the case of air, N2 is 1, sine 90 degrees. So let's just continue breaking this all down. We know that the sine of 90 degrees equals, what was it again? 1. Okay, you can use your unit circle to figure that out and prove that to yourself. I'd much rather have you not memorize that, but to actually understand it. Draw yourself a unit circle and work out why that's true. Okay, we have this. We have theta. We have these two components, you know, if you want to call them y and x. Think about what happens as you move this. If it's like a sweeper, think about what happens as you move it. That will help you understand why the sine of 90 has to be 1. All right, moving along. In this case, for a diamond, this is 2.4. So 2.4 times the sine of some angle that we're trying to figure out. If this equals 1 and this equals 1, this side equals 1. Okay? So what do we have to do next? Well, we have to go sine of our critical angle is 1 2.4. Okay? And then critical angle must be equal to the inverse sine of 1 over 2.4. So if we go ahead and we solve this thing, you'll find that the critical angle for a diamond is 24.6 degrees. So what does that mean in practice? Okay, if we have a diamond again, and like this, draw my diamond. What you end up with is you end up with a situation like this, okay? Light is entering the diamond from all sides, right? And this is why diamonds have their, you know, legendary sparkle. You get light entering from all sides. Now, if light strikes the surface of the diamond at any angle that is larger than the critical angle, then that light cannot escape from the diamond. So watch, if we put, incoming light here, right? 26 degrees is not very much. If you have a protractor, take it out and look at what 26 degrees is. Okay, anything larger than that magical 26 degrees causes the light to stay stuck inside the diamond. But you're like, well, how does that lead to a diamond looking sparkly to my eyes? What it means is light inside the diamond that does not strike the surface at a tighter angle than 24.6 degrees, I don't know why I put 26, can't get out. Well, this does. So what's going to happen is it's going to come shining out of the diamond like that. Okay, so you have all these angles of light filtering into the diamond. The diamond is cut in such a way that light will reflect off the back walls of it, the interior walls of it, and only come out the top of it. So it absorbs light from everywhere, but reflects it only out the top. If you ever look at the back of a diamond, it looks pretty dull. It looks like a dull gem, right? If you look at the top of a diamond, the part that they've cut to be visible, that's where it will be very, very sparkly. So you know, if you have someone in your house has an engagement ring that's been cleaned recently, this makes it a much better effect. Just investigate it a little bit. Look at the angles that they use to cut the diamond. Those angles are very scientifically specific. I'm not sure when people started cutting diamonds if they realized exactly that they're, working the refractive index. But your standard cuts of diamond are taking this into consideration, right? They're cut in such a way to maximize the sparkle that comes out the top. Does that make sense? And as a consequence of this concept of critical angle. One other place that I can think of where critical angle is important is in fiber optic cables. Okay, so if I have a fiber optic cable, okay, it's made of a flexible material with a fairly high refractive index. It's not super high, but it's somewhat high, and it's sheathed with something with a lower refractive index. And what ends up happening is because the refractive index is fairly high, light that you put in one end gets trapped inside the cable and travels its way along, internally reflecting off the walls, right? So it zips along, and you can even get fiber optic angles to carry light around fairly extreme angles. I think even above 90, well, 290 degrees anyway. Maybe not an instant 90-degree bend, but you can definitely get it to travel, through this way. Now, this is important in communications because, as we know, light travels, quite quickly, and you can, in effect, have information blinked on and off through a fiber optic tube or a fiber optic cable, and it gets from one point to another at the speed of light, which is, faster than, say, an electrical signal can travel. I should be careful with that. You can pass more information in a given amount of time this way by blinking the light on and off. Okay, so fiber optic cables work on this refractive index principle that you have some material with a high index and sheathed by a material with a lower index, and then you have a critical angle that's low enough that light never really gets a chance to escape from the medium. You pump it in here with a laser, you detect it over here with some sort of digital light detector, and you can pass digitized information through a fiber optic cable. This is the way that most information travels, at least on the larger kind of scale, like between continents and so on, and even from city to city. In some places, you can actually get fiber optic cables to your house to pass your internet traffic through, and the bandwidth of those things is amazingly high compared to, say, copper wire, or I think copper wire is the only other way really that I know of, either DSL or cable. It's much, much faster, much higher amounts of information can pass, and that's that.